I'm Hajaswaraya Emira binti Mashur, ID number 18002342. I will be presenting for process modeling and simulation part.
Hi, I'm Nopatin Fahana with ID number 18002426 and I will be explaining Reaction Engineering 1 part.
Hello, my name is Kwan Sukumar. My ID is 18002472.
Hello, my name is Moindran Murigetsu. My ID is 18002607.
Hello, my name is Nadiatul Izzah binti Saiful Yamin, ID 18002539, and I will be presenting PMS part.
The objectives for Reaction Engineering 1 course are as follows. For our group project, we were asked to design a reactor separator system for conversion of POME with a capacity of 50,000 tons per year to biogas of high quality. The average composition of POME are shown in the table. To convert POME raw material into methane gas, anaerobic digestion is chosen as the treatment process because of high yield of biogas while require lower energy cost. Reaction system to degrade POME into methane must include 4 stages of reaction in sequence, which are hydrolysis, acidogenesis, acetogenesis, and methanogenesis, which happen in 2 CSTR in series. The reason why we choose CSTR over batch reactor and PFR is that CSTR is simple to operate and have lower operating costs and maintenance, and therefore preferable for industrial scale of POME treatment. Table shown the operating conditions for first and second reactor, which include types of bacteria need to be existed in each stages to degrade the raw materials into more simple product, along with type of nutrients to be fed for bacteria, as well as to keep bacteria healthy. To maximize selectivity and yield and minimize site reaction, we need to control optimum operating condition for each reactor for it to achieve optimum production rate. Next is to use pre-treatment of POME before it enters the first reactor. Example of effective pre-treatment for POME that could result in high digestion rate and biogas yield are addition of ash and deoiling. Figure shows the rate of digestion and methane production with and without pre-treatment. To minimize site reaction, according to Le Chatelier's principle, water must be supplied in excess. For sizing of reactors, isothermal reactor is designed. First reactor requires 197.21 m3, meanwhile second reactor requires volume of 7,548.4 m3. So the total volume required for both first and second reactor is 7,745.61 m3.
The objectives of process modeling and simulation are to construct a comprehensive mathematical model of the reaction, to run a simulation to get better understanding of the procedure and compare it with the value from the manual calculation, and to observe the effects of various factors that will affect the efficiency. Chapter 3, Dynamic Mathematical Model of Reactors. Here you can see 2 CSTR in series, and for mathematical model, the overall mass balance is taken from m is equals to rho v and m is equals to rho f, and final equation is equation 1, and for component balance it is taken from n is equals to cv and v is equals to constant, and also v is equals to ac times hl, and we get equation 2. The rate law are as follows for each component in this process. And for reactor 1, the reactions of acidogenesis, these are the components mathematical model, and for reaction 2, for acetogenesis and methanogenesis, these are the mathematical models for the components in that reactor. And the energy balance for reactor 1 is shown here, dt1 over dt, and for reactor 2 is as follows, which is dt2 over dt. The steady state process has been simulated by using Aspen HYSYS software. Lists of the components involved were inserted, and the parameters obtained from Reaction Engineering 1 were utilized to do this simulation. The fluid package used is GCEOS. The feed stream has temperature of 55 degrees Celsius, pressure of 1 atm, and molar flow rate of 124.2 kg mole per hour. Volume used for each reactor is 197.2 m3 and 7,548 m3 respectively. The deviation error. The outlet molar flow rate of the second CSTR F manual is 176.6505 km per hour, and the outlet molar flow rate of the second CSTR F simulation is 114.5 km per hour. The deviation error is 35.18%. The end result indicates that the deviation error is in the middle range because the maximum percentage of an error to be considered small is 20%. There are a few possible causes that have led to this deviation error value. First and foremost is based on the assumption. The process undergoes an isothermal condition, but through the simulation on Aspen HYSYS, the assumption cannot be applied. Furthermore, since the majority of the values were derived from online articles and journals, some of the reaction engineering 1 properties may be less precise. And the approximated and predicted values can be improved with better parameter and property of values from a more reliable and closer to the experiment values.
To carry out sensitivity analysis on the simulation, pressure, temperature, and flow rate were manipulated at the inlet stream. The data from HYSYS software is obtained and recorded. In sensitivity analysis for pressure, it was observed that there were no dramatic changes to the conversion performance as the pressure was manipulated. It is assumed that there were some errors in the simulation as we are not able to see pressure effect on the conversion. However, for reactors that operate on POME, the pressure should be low. This is because with low limited pressure, the production processes can be thermodynamically enhanced. The effect of molar flow rate on the conversion was also observed. From the data collected on the process simulation in the software, varying molar flow rate at the inlet stream caused a change in the conversion performance for reaction 1 and also in reaction 3. The conversion percentage for reaction 2 is remain unchanged as the feed molar flow rate increased. Based on the graph, it shows that the feed flow rate is inversely proportional to the conversion, hence lowering feed flow rate will increase the production. Lastly, temperature ranging from 20 degrees Celsius to 100 degrees Celsius was used to investigate its relation to the conversion performance. Reaction 1 shows an increase in conversion percentage when the temperature increased from 20 degrees Celsius to 40 degrees Celsius. On the other hand, the percentage conversion seems to be decreased after temperature 60 degrees Celsius. Reaction 2 shows no change in conversion percentage as the temperature increased. As for reaction 3, the conversion performance is decreasing along with the increment of the temperature. From the graph, we can deduce that the conversion performance has peaked somewhere in between 40 degrees Celsius and 60 degrees Celsius. This information correlates with the knowledge that treating palm oil mill effluent with thermophilic temperature generates higher gas when compared to using mesophilic temperature. Also, thermophilic temperature is 55 degrees Celsius, which is situated in between 40 degrees Celsius and 60 degrees Celsius.
Objectives for this IDP is to propose a separation process that will produce biogas that meets the requirements, to demonstrate the efficiency of the double bed pressure swing adsorption PSA method for biogas production, and also to devise a strategy for producing biogas from various waste materials to the greatest extent possible. This falls under separation process. So it is safe to say that it is easy to predict that there are major risks associated with operating a biogas plant. In this IDP, we are going to talk about various hazards such as hazardous substances, electrical hazards, and also mechanical hazards. Next, we are going to talk about maintenance. The PSA vessel and piping contain flammable and potentially toxic gas during normal operation. It is critical to thoroughly purge the PSA system with nitrogen so that we can prevent the formation of a flammable mixture before the PSA system goes to service. If there isn't enough time for successful purging at low flow and pressure pumping may be needed, which means an external pump will be needed. So this is quite tricky because the maintenance can be risky. Next, we are going to talk about the cost. So the total cost of installing an AD biogas plant varies depending on the feedstock. For example, what would you want to yield? For example, corn, maize. Okay, the most expensive part of an AD biogas plant is the digester system. So the biogas system also can be upgraded by various modifications. We will talk about the modifications more in our IDP, and also there are a lot of upgrades you can do so that your end product will be higher, and which means more upgrades cost you higher maintenance.
The challenges that we faced in selecting the PSA system. Firstly, high capital costs. The solution that we suggested for this problem was shorten the total cycle time to overcome this challenge. Secondly, carbon dioxide, the use of carbon dioxide. We suggested to reuse carbon dioxide to cultivate microalgae. After that, the size of the bed. PSA process requires a large bed to obtain a great amount of purified biogas. Fourthly, the last challenge that we faced in selecting this PSA system was implement a sophisticated task. So the solution that we thought of for this problem was implement with modern technologies by modeling different aspects such as aspen and stuff like that. Then there is the strategies to maximize the production of purified biogas, gases from products of biogases. So firstly, we suggested a strategy which is use an absorbent with a higher cyclic capacity. Then we suggested another strategy which was use radical columns. After that, we also suggested implement enhancements and strategies for monitoring. Then we suggested two other strategies, which were increasing the bed length and utilizing multi-stage absorption techniques.